So today we're talking about conditional probability and the idea of independence. So let's kind of define conditional probability and what it is, although you did see it in chapter 1. So there's this idea that the probability we assign to an event can change if we know that some other event has occurred. And this idea is really key to a lot of things, a lot of applications of probability. So if we know one thing that might inform something else. So we say conditional probability is the probability that one event happens given that another event is known to have happened. So the probability that one event happens given that another event is known to have happened. The conditional probability that event B happens given that event A happens is denoted by probability of B given A. So we have this new symbolism that we're going to be using. Right? So probability of B, and then this line here means given A. So it's the probability of B given A, or I could have the probability of A given B. And all that means is that it's the probability that B happens knowing that A already happened. So think of that, read that line as given that, or under the condition that is a good way to think about that line. So I know you're getting sick of this data. We've seen that table before, but this is what we looked at before, and I just wanted to remind you, we're not even going to really deal with numbers here. So looking at the idea that given that a senior voted no to uniforms, what's the probability, or given that a student voted no to uniforms, what's the probability that the student is a senior? So thinking about that, given that a student voted no, I am eliminating everything but the no's now. And so I'm going to look at senior and no, so that 102 number, and then it would be divided by the total no's, 196. So that's given that a student voted no, that would be the probability that a student is a senior. So that would be 102 over 196. Right, but then if we're looking at given that a student is a senior, so given senior, so we know that they have to be a senior, so everything else goes away. What's the probability that the student voted no? So now I'm looking at 102 divided by 159. Okay, so that's this one. And that's this one. Again, these are things that we've done before, right? But we have different notation for them this time around. So now that we know what conditional probability is, we can work to calculate it. Here's the deal. If I have a two-way table, that's nice, that's wonderful. Two-way tables make things really easy for conditional probability. However, a lot of times we will not have a two-way table. So we need to know how to calculate a conditional probability given different probabilities. So to find the conditional probability of A given B, we're going to use this formula. So remember that line means given. So the probability of A given B, that's our conditional probability, is the probability of A and B divided by the probability of B. And we have our new fun symbol here for this intersection, like when A intersects B. So remember that fun symbol means the probability of A and B over the probability of B. If you like it in words better, it's the probability that both events occur divided by the probability that the given event occurs. Okay, so this is a formula that you do use a lot. However, you do have it in the Blue Book in your formula sheets, so that's nice. They write it with intersection. They write it with intersect, but it's still really nice. So this is a formula that we are going to use a lot. So if you haven't already, make sure that you write this down, just so that you know that this is something that we will use. Okay, hopefully I've given you enough time to write it down. Okay, so let's try a problem. So looking at this, the problem in 1912, the luxury liner Titanic, on its first voyage across the Atlantic, struck an iceberg and sank. Yes, yes, we know. Some passengers got off the ship in lifeboats, but many died. Suppose that we randomly selected one of the adult passengers from the Titanic, and we're going to define our events, right? And I've mentioned this before. A and B are really hard to use because you don't remember what A is or what B is. So I'm going to define the events as F is first class passenger, S is survived, and T is third class passenger. Okay, so we are going to first try to find what's the probability that someone so probability of T given S. And it says interpret this value in context. So first let's put that into words. We want the probability that someone was third class given that they survived. So what's the probability that someone was third class amongst the survivors? And we want to interpret this in context. So what I'm going to do is give you a slide with this, with the numbers a lot larger so you can actually see it. And then I want you to try to do this with your neighbor friend. So here's the table larger so that you can see it. Again, you're looking for the probability of third class given that someone survived. So I want you to try to figure this out, and we'll pause the video so that you can solve this problem, but I want you to try to solve it with the person next to you. And then when you think you got it, we can start the video again. Okay, so we're back here where the numbers are a little bit smaller, but I just wanted you to be able to see the whole problem. So we have written down here, we have the probability of third class given that someone survived, right? So that's kind of what we're looking at when we're doing this. So first thing I'm going to do is just highlight survived. So since it's given survived, I'm just looking at those that survived. And then I need to specifically look at third class given survived. So I'm going to pay attention to the third class. So I'm going to do 152, and that is the number of third class passengers who survived, and it's going to be divided by my total number of survivors. And I got a probability of 0.342. But that wasn't the whole problem. It says interpret this value in context. And you're going to see this a lot in stats. Interpret this value in context. That means I have a number here, 0.342. What in the world does that number mean? Is it the number of apples I've eaten? Who knows? So we always need to say what the number means and kind of how to, like if I just said it's the probability, people be like, the probability of what? So I need to explain what this number is and what it means. So the way that we would interpret this value in context, what I would say that given that the randomly chosen person survived, there's about a 34.2% chance that he or she was a third class passenger. So I've taken the number and I've put it in words that people can understand a lot easier. That's what I'm doing when I'm interpreting the value in context. Given that the randomly chosen person survived, there's about a 34.2% chance that he or she was third class passenger. Now you're probably saying, Ms. Shope, you said solve for probability. You told us probabilities are decimals. Why are you, reporting this in a percentage? Great, yeah. Because when I'm interpreting a value, again, people don't usually, if I say, oh, there's a probability of 0.34, people are like, what? But if I say there's a 34% chance, people go, oh, I know what that means, right? So when I interpret in context, we tend to use percentages, not just me, but statisticians tend to use percentages again because part of stats is making numbers accessible for people, and people understand percentages more than they do decimals. Is it wrong to put a decimal? No, it doesn't make as much grammatical sense if I were to explain it that way. So it makes more sense to explain it in percentages. So that's what I would like you to do when it says interpret this value in context. Okay, let's look to the next portion of the problem. Given that the chosen passenger is not a first-class passenger, what's the probability that he or she survived? Okay, write your answer as a probability statement using correct symbols for the events. Ooh. So to come up with the symbols, what I first have to do is kind of go back to what the events were. So I have three events: first class passenger, survived, and third class passenger. This says, given that the chosen person is not a first class passenger. So that means they could be second or third. So I'm looking for not first class. The way that I write not first class is I say first class's complement. Right? And probability that she survived, I'm going to use the S word for survived. Right? So first class passenger complement, right? So not a first class passenger. So given that the chosen person was not a first class passenger, what's the probability that he or she survived? So we have to think about which one goes first. Okay, so given that they're not a first class, so it's going to be S given F's complement. So I'm looking for the probability that someone survived given that they were not first class. Okay, so this is what I'm actually looking for. And this is really the first part of the problem, is figuring out what are those symbols that I should be using. Okay, I'm going to show you the chart again so you can start working on this with a neighbor friend. Okay, so as we determined before, we're looking for the probability that someone survives given that they were not first class. Okay, so a little bit trickier, this one. So again, work with your neighbor friend to figure this out. And then once you've got it, you can start the video again. Okay, if you think you've got it, let's take a look. So what makes this one difficult is when I'm looking at not first class. We haven't done this before, but it's going to involve two different things, right? Second and third class together. So that makes this a little bit tricky, but this is why I went ahead and highlighted. I know it's hard to see in the back, but I highlighted both second and third class so that you can see what I'm talking about. So we already figured this out. It's the probability of S given F's complement, or survived given not first class. So I'm really going to be looking at these numbers here, those that survived out of second and third class. So the first thing I need is that number. So I need to look at who survived in second and third class. Okay, so where did these numbers come from? So I took those that survived, 94 and in second class and 151 in third, and I'm going to add those together, 94 plus 151. And then the number of not first class, as in first class's complement would be my total in second and my total in third. And again, because these are, I'm dealing with both second and third class, I'm going to add these together. So my total that I'm dividing by, my given probability, is going to be 261 plus 627. So that adds up to 245 divided by 888, and I get a probability of 0.28. So in this particular case, there's a 28% chance that someone survived if they were not a first class passenger. So now we need to talk about a really important concept called independence. And independence is super important in statistics. All right, so two events are independent if the occurrence of one event has no effect on the chance that the other event will happen. Now, this is pretty rare for something to be independent, but occasionally it happens. A great example of independence would be a coin flip. If I flip a coin, there's a 50-50 chance of it being heads. If it's heads first and I flip a coin, that does not mean that the probability is going to change for the next coin flip. The coin has no memory. Each individual flip is a 50-50 chance, right? So each coin flip is independent of the other. The probability does not change if I know that the first flip was heads. That does not change the probability for the next flip. Those events are independent. Okay, so let me give you an example with playing cards to kind of help explain independence. So, hi, doing a little cameo here so that you can see a little demonstration I'm going to do with the cards. So, to talk about the best way that I can do this is say, okay, I have a card here. You don't know what it is. Place bets. Is this card red or is this card black? Okay, and again, we have to have some cultural competency with cards. We know that there are 52 cards in a deck. Half of them, 26, are red and 26 are black. There are 4 suits, right? 2 of which are red and 2 of which are black. So again, what do you think? What is this card? Okay, so since you can't see the card, you don't know. You've got a 50-50 chance that it's red or that it's black, right? So 50 chance, that's the probability that it's red. Now I'm going to say this card, I'm literally looking at it right now. This card is a spade. What is the probability that it's red? So now I have the conditional probability of, given that this is a spade, what is the probability that it's red? And you can say 0. Spades are black, of course, right? So you know that there's a 0% chance that this card can be red because you know that it's a spade, right? These are not independent events. Knowing something, knowing that this is a spade, suddenly tells me whether or not this card is red or black. The probability changes. Okay? So red and spade are not independent. Let's pick another card. Ooh, another card. Ooh, I'll turn it upside down so you can see Sue. So I'm picking another card here, and I'm going to again ask you for red or black. What's the percent chance that this card could be red? And you would say there's a 50% chance. Half the cards are red and half the cards are black. And I'm like, okay, now I'm going to tell you something about this card. This card is an 8. What is the probability that it is red? Okay, now if you think about this, there are 4 8s in this deck. 2 are red, 2 are black. 2 out of 4 is still a 50-50 probability. So knowing that this card is an 8 does not change the probability that it's red. it's still a 50-50 probability that it's red before I knew it was an 8 and after I knew it was an 8. The probability didn't change, then red and being 8 are independent events. One does not inform the other. Knowing that this is an 8 does not change the probability that it's red. So these events are independent. And that's, I think, one of the easiest ways to think about independence. It's a really tough concept. We'll talk about it a lot. But looking at this idea that knowing something, if something is independent, that means that if I know something is true, given something, does not change my probability. So again, to have it written down in words, A and B are independent events if knowing whether or not one event has occurred does not change the probability that the other event will happen. So there's a way that we can write this. The probability of A given B, so the probability of A a probability of A given that B has happened is equal to the probability of A given B's complement, and also equal to the probability of A if the event is independent. Okay, and I could do it the opposite way too. Alternatively, events A and B are independent if the probability of B given A is equal to the probability of B given A's complement, which is equal to the probability of B. So what we're going to have to do is kind of do what I did with the cards and prove this mathematically. I'm going to have to say what is the probability of A given B, and does it equal the probability of A? So whenever a question asks, are these events independent, they want to see math. Okay, not just, oh sure, I'm sure that matters. Like, of course, most things matter, right? But I need to prove this mathematically. Now you're probably like, okay, well, how close do they have to be? I mean, they have to be real close, like 50% and 50%. Real close. Most things are not independent, right? Knowing one thing usually informs me about something else. Really only random chance events are independent. There's a couple of other times. So what I like to do for math, because that's hard to think about all those things and you aren't given these formulas, is I just say, look, the probability of A given B has to equal the probability of A. Or the probability of B given A has to equal the probability of B. If I can prove either of these equations to be true, then I'm good and the thing is independent. So this is what I'm going to use, either this top one or this bottom one, right? So I'm either going to use this one here or I use this one here. Sometimes, I use both, but really you only need one to prove independence. Let's try it. Right. So are the two events male and pierced ears independent events? In other words, does knowing a person's sex tell us something about the probability of whether or not they have pierced ears? And of course, the textbook used the wrong term again, as will the AP exam. So, look, I fixed it. So does knowing a person's sex tell us something about the probability of whether or not they have pierced ears? Now, it doesn't matter to me if you do A given B or B given A. You get to pick what it is. So you could prove the probability of sex given pierced ears or pierced ears given sex, and then look at the other probability. So I'm going to have you pause it here so that you can work with a neighbor friend with this chart to tell me, are these two events independent? And then when you think you've got it, let's come on back. So I defined pierced ears as event B and male as event A. So, with that terminology, I looked first at given male. So I ignored everything but the males for a second, and I did what's the probability of pierced ear given male? So B given A, if we were looking at it like that. So I looked at it and I was like, oh, that's 19 out of 90. So that's a 0.211 probability. Okay, let's compare that to the probability of just pierced ears. So I looked at this column because I'm not looking at a conditional probability. And I said, okay, what's the probability of just pierced ears? So that would be 103 divided by 178, and that's 0.579. And we can see that those are very different numbers. So that means, yeah, if I know that if I know someone's sex, I know whether they're more likely to have a piercing, right? So knowing a person's sex influences their piercing. So I would say knowing that the chosen student is a male changes or greatly reduces the probability that the student has a pierced ear. So these two events are not independent. So that's how I would prove whether or not something is independent. Here's the last example that I want you to try, and I'm going to have this up so that you can look at, or maybe you can pause it so that you can look at this chart here, and then I'm going to write the answers at the very end of the PowerPoint next to these slides on the OneNote. But I want you to actually do this whole thing with your neighbor friend, just to try and see, make sure you've got this down. So what we're wanting to find out is about graduating from high school and owning a home. So if we know that a person owns a home, what's the probability that the person is a high school graduate? That's the first thing I want you to do. If we know that the person is a high school graduate, what's the probability that the person owns a home? And is being a high school grad independent from owning a home, aka our A and B independent events? So try this and then check out the answers on the OneNote, and then you can go ahead and start your homework. Have a great day.